Hello. This is Math 141 review session. Hopefully the lighting is okay. All right. So here we are. I hope everyone's okay out there. So we can start with a problem that I haven't continued, I haven't done during class, right? So it's going to be on the intermediate value theorem. And the intermediate value theorem is simply a theorem that utilizes continuity of functions to basically say that there is a number in between two numbers that makes the function equal a certain value. Okay, so let's look at an example, right? So I think I gave one of the problems. One of the problems was x cubed minus 3x plus 1 equals 0, right? And I want to show, so what makes this a little different from other problems in that you may have been used to is that we're not looking for a number as a solution. We're looking for a statement. We're looking for a statement that demonstrates, or statements that demonstrate a certain result. And so what are we trying to show, right? That's what we're trying to do. We're trying to show that there is a root to this, or I should say, there's this root, or I should say solution. There is a solution to above polynomial equals 0 to 1. So this is what I want to show. I want to show this statement to be true. I want to show that there is, so this statement here, there is, it's a very, very powerful statement, right? To say that something exists. We're trying to show that something exists. And what is it that thing that exists? It's the solution to this equation. And we're saying that this solution lies between the interval 0 and 1. So forward procedural steps, right? And what's nice is that this polynomial, and what we know, what we've been learning in class, is that polynomials are nice functions because they're called smooth, or in other words, they're continuous, right? When you draw a polynomial on a graph, when you draw it, it's a fluid connected line. And so I want to say, hey, there is a number between 0 and 1 that when I plug it into this equation, I get exactly 0. Now, am I trying to actually find what that value is between 0 and 1 that makes the solution equal to 0? No. I can, though. I can using my graphing calculator. But am I trying to do that? I'm not trying to find what it is. I'm just trying to show that there does exist such a thing. So that's what we're going to do. Now, first I'll give you the visual representation of what we're going to see. And then we're going to set up the statement that does show it using the intermediate value theorem, and then we're done. And there's not much else to say. So this is a cubic polynomial. So this is a cubic polynomial, and we kind of should know what cubic polynomials look like, right? The most important thing is that the cubic polynomial, or polynomials in general, are continuous. The intermediate value theorem is based upon the fact that the function that we're talking about is continuous. If the function is not continuous, there's no need. This theorem is not applicable. Okay, so what's fundamentally needed is that the function that we're dealing with, and in this case, we're dealing with a polynomial, it's continuous. So since it's continuous, meaning that it's a smooth curve throughout, it's connected throughout the graph, then this intermediate value theorem does apply to it. Okay, so what does the visual look like? Well, I'm interested in particular with the interval 0 to 1. So what am I going to do? I'm going to say this. I'm going to let my function f of x equal x cubed minus 3x plus 1. So all I'm doing is I am letting this polynomial here, I'm making it my function f. And what I'm going to do is I'm going to say what happens to my function at 0. So where's f of 0? F of 0 is 0 cubed minus 3 times 0 plus 1, which equals 1. So I got 1 when I plug in 0 into my function. And then the next thing I want to find is what happens at 1. So I'm looking for what happens to my function. What are the values of my function at the endpoints of my interval, 0 to 1. So f of 1, when I plug it in, I get 1 cubed minus 3 times 1 plus 1. And then I get 1 minus 3 plus 1, which you get what? You get 1 minus 3 is negative 2 plus 1 is negative 1. So these are two important things. So what do I get? From here, I get that f of 0 equals 1. And what do I get from here? I get that f of 1 equals negative 1. And this is all I really need. And now if I were just to give you the visual, right? I'm going to draw it over here. Maybe I should make this a little... So I got from at 0, my function is at 1 somewhere, right? At this point, it crosses the y-axis at 1. And at 1, my function is negative 1. So far, I've only plotted the points of my function at 0 and at 1 respectively. Now, what did we just say in the beginning? We said that my function is a polynomial, and we know that polynomials are what? Continuous. And what do we know about continuous functions? We know that if I were to plot the graph of a continuous function, I have to draw it in such a way that what? That I can't lift up my writing utensil, instrument, marker, pencil, and whatnot, right? So what would happen if I were to draw a curve or a line, or how would I go from here to here if it's continuous? That means that I have to, some way, somehow, not sure how, but I have to, what? I have to cross the x-axis somewhere, right? So this is exactly, this very picture indicates what's called the intermediate value theorem. If I have a function that's continuous on a interval, and the endpoints of my interval, my function is above the x-axis, below the x-axis. In order to connect those 2 points, I have to cross the x-axis, which means what? Which means that at this point, whatever that point may be, that point right here is the solution. So I'm gonna call this point, they usually use like C for that point. So there is a, so this means there does exist some value C, some constant, in interval 0, comma 1, that such that, so we like using the term such that a lot, such that f of c equals 0, which means what? It means that there's a c value, or there's a value between 0 and 1 that is the solution. In other words, c is the solution, or I should say root, of cubic polynomial. And so this, all of this together, put together, is the intermediate value theorem. So in a way, it's a very simple idea, right? It's a simple idea, but at the same time, it's quite a profound concept. And this idea of continuity is extremely important to have a grasp on. So then, putting this all together would be the intermediate value theorem. So how would I say this as a final answer, right? So you can basically, I'm just going to summarize everything into one whole statement. That's the idea. So we would say, since f of x equals x cubed minus 3x plus 1 is a continuous function, and I'm going to specify the interval on interval 0, comma 1. So I'm specifying the closed interval 0, comma 1. So since my function is continuous on this interval, right? That's the first requirement. It's a continuous function on the interval. The second requirement is, so it says, since the function is a continuous function on the interval 0, comma 1, and f of 0, which was what, 1, is above 0, and 0 is above f of 1, which we found to be negative 1, right? So since it's continuous and at the endpoints my function is above 0 and below 0, then by the intermediate value theorem, there must exist a value c in the interval 0, comma 1 such that f of c equals 0. And I am done. I am done. I have invoked the intermediate value theorem based upon the condition that my function is both a continuous function, and at the endpoints there are one of the endpoints, the value of the function is above the above 0, and the other endpoint, the value of the function is below 0. And because it's continuous and because of these endpoints, there has to be some point in between that crosses that x-axis, and therefore I have shown that there's such value does exist. And so that would be a complete response to showing that a solution does exist. So that's in this live stream on this beautiful Sunday night. You can either ask me questions about this or any other questions that you may have. So Adam asks, do you have to find that x value? So for now, I'm not asking you to find it. I'm just asking you to show me that there does exist. So for now, I'm just asking for, at least for on the exam tomorrow, I'm just asking you for this statement at the end. Because finding the x value, right, you could do that And that just requires you to know how to use your calculator. To find the intersection point or to find the zeros, your calculator, TI-84, 83, and any other of those calculators can find you what that X value is. And that's cool to get, right? But what's more important to me, at least for now, is that you guys understand how to, in words, say that there is such a value, not necessarily that what that value is. Because you've done that already in algebra 1, algebra 2. You found this all the time. I'm not interested in that so much. I'm interested in expressing this idea, which is something a little different. Is average velocity going to be on the test? I don't, as of right now, no. Average velocity will not be on the test. Can you do a problem with sine and cosine? Yes, I can. Or is only sine going to be on the exam? So you can expect any kind of trigonometric function. So I'm going to do that now. Yes, I'll go over the, so first I'll go over the sine and cosine limits, right? And then I'll go over the discontinuity, continuity stuff with piecewise functions, okay? So thank you for those questions. Hopefully that helped. And hopefully this helped. So let me know in the comments, was this helpful in understanding how to do a problem? Do you have to restate the IVT word for word? Yes. You do your best in restating it. Great, thank you. Thank you for those of you who said yes. So yes, basically you're just restating the theorem, but you're restating the theorem. You're restating the theorem with respect to the function that you're given, and with respect to the interval that you're given. So you may be given a different interval, and you may be given you will be given another function. And so I just want you to be able to given the different function, right, and given the different intervals, just to set this up and basically you're restating the intermediate value theorem. Okay, great. So that's one. And there are other problems. There are other problems that will not give you, for example, this is quite a simple problem, because there might be other equations where you have an equation that's not equal to 0. And I'm may ask you, how do you apply the intermediate value theorem to show that there isn't a solution, right? So basically what you would do in that case, so let's say, so I'm gonna give you just a different taste to this. So let's say I had something like this, right? X cubed minus 3x plus 1 equals, let's say, like x squared plus 2x, right? Or something like that, right? So let's say I want to show the equation on the interval 0, 1, right? So let's say I have this as my problem. Well, then at this point, I want to show that there's a solution, right? And how do we normally solve a polynomial equation? We set it equal to 0. So basically, for these kind of problems, you have to do one step before doing these steps. You would have to set the equation equal to 0. So you have to set equation equal to 0 first. So you would set the equation equal to 0. So you would subtract x squared. You would subtract 2x, right? And then you would have a new function. So my new function would be what? What would be my new function? It would be x cubed minus x squared minus 5x plus 1 set equal to 0. So now I have this scenario. And then I'm going to say this is my function f of x. And then I'm going to plug in 0 for this and a 0 for and then 1 to this function, and then see the values, and then apply the intermediate value theorem. So if you get something like this, all you have to do is set it equal to 0 and then start from there. So it's not much of a difference, except that you have to do just a little bit more work, which is not really much, before starting the intermediate value theorem process. All right, so that's all I wanted to say about that. I think we're good with that for now. So what I'm going to do right now is a limit problem, and I think I'm going to use one of the problems that I posted on Blackboard. I need a better eraser. So I think I'm gonna do one of I'm gonna do one. I think a problem that you guys had on your homework. You had a problem, so I want to evaluate limits. Now I believe this might be the hardest limit problem that you've seen uh, in your homeworks using trigonometry. And there's one that says sine of theta. So limit as theta goes to 0 of sine of theta over theta plus tangent theta. And yes, Adam, IVT is only used for continuous functions. Only for continuous functions. IVT, continuous. Continuous functions, IVT. All right? Okay, so I think this is one of the problems that you guys had in your homeworks. And personally, I think this might be probably the hardest one you've probably seen. And the only reason why it's hard is because you may not, it's not so apparent what to do, algebraically speaking. Because a lot of these limits that you're evaluating, right? I'm requiring you to evaluate them algebraically. So on the test, you'll be asked to evaluate limits using tables, and then you might be evaluating limits using seeing a graph, and then you have to be able to evaluate limits using um, algebra, either factoring, simplifying complex fractions, rationalizing denominators, absolute value problems, and trig, right? And so remember when we deal with trig, one thing we had to know is that the limit as theta goes to 0 for sine of theta over theta, this equals 1. So this is like, if I don't have this, I can't really do much. I think it might be a little too bright. Is there a question with tan on tomorrow's test? Maybe, possibly. Gotta be ready. How many questions will be on the exam? How many questions? So that's kind of like a tricky one because what does it mean to have a question? Like basically, it's very simple, right? Don't worry about how many questions you have. Worry about the topics that will be covered. So what have we covered? We've covered limits quite extensively. What do we need to know for limits? How to evaluate them? Using the table of values. You've seen that. To learn how to find limits, given a graph, seeing where you have open holes, where you have jumps, where you have asymptotes, right? So you've seen that. You should be able to find limits using algebra. We've seen that. And we've also discussed continuity. So finding different kinds of discontinuities, right? We've talked about removable, jump, and infinite discontinuities. Being able to recognize those algebraically, graphically, and then we have the intermediate value theorem, and then we have finding the values for a and b or for different constants, right? That make my piecewise function continuous. So those topics, as long as you know how to do those, I'm going to give you basically I'm giving you at least one problem for each topic. So if you can enumerate the topics that we've had, that will give you the roughly how many questions you will have to do tomorrow. Okay. So first we're going to do this, and then we're going to continue with the. Yes, Khan Academy is very good. At least for like introductory topics, it's pretty good, and they have a lot of videos. So you can resort to many different videos on YouTube. Just don't go too crazy with finding videos because there might be too much information, right? Don't flood yourself with information. As long as you're able to complete yourself with the pen and paper, you should be okay. All right. So now the question is, how do we do this, right? How do we proceed here? And this problem right here, we're like, I don't know, maybe I don't know what to do. But what do you know? What do you know about sine, cosine? Well, I know that sine theta over theta equals 1, right? But what's the problem here? This theta is attached to the tangent by a plus sign. So I can't just say, hey, this equals 1, and then just get rid of the sine theta over theta. I can't just do that. So what am I going to do? I'm going to do this instead. I'm going to rewrite. So a lot of this is just rewriting algebraically. I'm going to rewrite sine theta over theta, and I'm going to rewrite tangent. I should know what tangent equals in terms of sine and cosine. And normally, we try our best to simplify tangent as sine and cosine. So I can write this as sine of theta over cosine theta. So all I'm doing is I'm going step by step. I went from tangent, and now it's sine over cosine. So that should be okay. And then we're going to continue. So the limit of theta, as theta goes to 0, is what? Sine of theta over. Now, what kind of expression do we have here? This here is a complex or compound fraction. And I have a fraction, then I have a fraction within it. Now, normally, what do we do with these fractions? We try to make them into a single fraction, right? So what's missing here? I'm missing a cosine theta. So I'm going to multiply theta and over 1 by cosine theta over cosine theta, and then I get theta times cosine theta over cosine theta plus sine theta over cosine theta. So again, I'm going from this step to this step to this step. All I have been doing is algebraic steps. The first step, I rewrote tangent to sine over cosine. The second step, I made my denominators in the lower denominator, right? My fractions here in the lower denominator, I made them the same. And since I made them the same, now I can do what? I can unite them, and I get the limit as theta goes to 0 of sine of theta over theta times cosine theta plus sine theta over cosine theta, right? All I did was I united the fractions into a single fraction. And now I have a fraction divided by a fraction. And how do I divide fractions? I multiply by the reciprocal, and I get the limit as theta goes to 0 of sine theta. So I'm going to just write this over 1, multiply by cosine theta over theta times cosine theta plus sine theta. And so now you may be thinking, okay, we're doing all this work, but why? Will I see the light at the end of the tunnel, basically, right? That sometimes we don't know if it will work. But in this case, things will work out. So here, theta goes to 0 of sine theta multiplied by cosine theta all over theta times cosine theta plus sine theta. Okay, so we have a lot of sine, cosine, theta, tangent, like we have a lot of these sine, cosine, tangent things, right? Okay, so just responding to Janae, do we get marked by each step, just the answer, or both? So, of course, the answer is important, right? I want to be able to see that you're able to get the answer correctly. But if I just see the answer and there's no work, then I'm not. It's not going to be. It's not. I'm gonna ask you, where did you get your work from? Like, how did you get the answer? So, do your best in providing every justification for your answer. Okay. And yes, I will be asking to name the kind of continuity. Discontinuity, not continuity, is just one kind of continuity. But the discontinuity, um, you should be able to recognize what discontinuities exist. Okay. So at this juncture, you're like, okay, I listened to you, right? I listened to everything you've said. I've done it. I've wrote it down, and then I'm here. But then you're like, what do I do? How can this help me? How can this be any better than what I started with? Well, that's where I said, where I've been saying, and I say this to a whole bunch of students that I've taught, is that your algebra has to be your algebra skills, particularly for calculus, it has to be pristine, right? It has to be pristine, meaning that you should be able to recognize things algebraically and see, okay, you know what I can do? Look what I can do. I'm gonna write this over here. This is the limit as theta goes to 0. Now, what algebraically what I want is that I want this to appear somewhere. I want sine of theta over theta to appear. I want it to appear somewhere, right? So then I'm like, I have this sine theta here, and I have this theta here. But the problem is this theta here is attached to this cosine theta. Now, this is where I guess when you have more experience, you're able to do this. You're able to see that I can do the following. What I could do is factor out the theta. And I'm factoring out the theta out of this denominator. And I can factor out the theta out of this term, right? So I'm left with what? Cosine theta plus. But then you're like, wait, but there's no theta except for this theta here is within the sine, so I can't just take out the theta. But this theta here, how can I factor theta out of this? Well, what I could do is do this. Sine theta over theta. And then you might be like, but where did this theta come from? Well, what I did was I factored out the theta out of this whole expression. I factored it out, meaning that if I distribute this back in, I should get this back, shouldn't I? And if I were to distribute the theta to cosine theta, I get theta times cosine theta. And if I distribute the theta to sine theta over theta, the theta is canceled, and I'm left with this. So from here to here is a complete legal move. Now you're like, oh wait, how does that help though? Because now look what I could do. Look, don't you see that you have sine of theta over theta here? And you also have it here. I see sine of theta over theta in two places. And the limit is approaching 0. And what do I know? The limit as theta approaches 0 of sine of theta over theta equals 1. So then sine of theta over theta, this goes to what? 1 as theta goes to 0. And sine of theta over theta equals 1. So then, in a way, this here and this here, I can kind of just consider it as 1, because that's what the limit of this expression approaches. And now I can write this as limit of theta goes to 0 of cosine theta over cosine theta plus 1. And so now this is a lot better than what I had. And then, now what can I do? Can I plug in? I could definitely plug into this. I could plug in theta with 0. And when I plug it in, I get cosine of 0 over cosine of 0 plus 1. And I get 1 over 1 plus 1, which equals 1/2. So the limit to this, the value of the limit of this expression is 1/2. And like I said, this is probably the hardest one of the limits. So if you're able to understand how we get to this limit, right, all the other limits should be much simpler. Why is the 1 in the denominator? Well, this one here, it comes from this expression. This limit, the limit of sine of theta over theta, that's why I crossed it out, but I'm crossing it out with a 1. This whole expression here goes to 1. It becomes 1 using the limit. So this is why limits are like a different kind of species in terms of operations, right? It's like a little different. It's not functions. You're not evaluating them. You can evaluate them by plugging them in, but it's a little different. In this world of limits, things behave just a little different. So I can say, hey, this whole thing, as theta goes to 0, this whole thing is 1, because I know it's 1. So instead of writing sine of theta over theta, I can just say this equals 1. using the limit. So it's kind of like a little mysterious, right? But that's why this 1 is here. It's because this expression in the denominator, as the limit of theta goes to 0, this equals 1. And then I can forget about this sine of theta over theta as well, because this whole expression here is basically, like I'm saying, I'm multiplying by 1. And then what's left? Cosine of theta over cosine of theta plus 1. Now, at this step, I can just plug in theta with 0. And then at this step here, cosine of 0 is 1. So 1 over 1 plus 1 is 1/2. This is a nice limit to try to figure out because of the algebra that's required. So, any questions about these steps? And even if you don't understand this completely, just try to see every step and try to consider every step. Is every step okay? And then see which step here you're kind of like maybe not clear upon, and then try to think why it's okay, why I'm able to do every step. And once you're able to see that clearly, then you're like, oh, it should be all good. But again, the most fundamental thing, the most fundamental skill that you need to have it completely sharpened by now is your algebra skills. And the most crucial part was from here to here, was this step here, was factoring out the theta. Normally people wouldn't be able to see that, right? So that's the hardest part. Besides that, everything else is things you should be able to see. Can I bring the board closer? Let's see. Hold on. This is kind of let's see. Is that better? Is that close enough? Hopefully it's close enough. Okay, great. Yeah, just let me know because this is, not the most ideal setup that I can possibly conjure up at the moment, but this is what I'm able to provide at the moment, right? Hopefully next time I have no, not hopefully, I will have a better setup. But for now, this is what we're able to do. Okay, so boom, great. Now, if I look back at the comments, we did IVT, we did limit question with sine and cosine. And so now we're going to do a problem using finding the values for piecewise functions, right? And then after that, we'll do absolute value limits, okay? So I'm going to go back to, and again, I think this is posted. I posted this on Blackboard, the solutions, but I could definitely give you a real-time play-by-play of how to approach finding values for piecewise functions to make them continuous, right? So there's a problem that I gave you. It's h of x. So h of x is 2x. And then I have ax squared plus b. And I have 4x. And if x is less than, is it greater? If x is greater than 2, and this is if x is less than or equal to 2 or greater than or equal to 1. And 2x is if x is less than 1. Okay? So this is a piecewise function. And again, what are piecewise functions? They are functions that are composed of different pieces of other functions. And you kind of splice them together. And we write it in a very strange way. It's a little strange. But the idea is that these if statements, right, they're conditions. And if this condition is met, which means that if x is less than 1, then my function assumes this expression, and so on and so forth, right? And the idea is I want to find, so my goal is, what's my goal? My goal is to find values for a and b, because I want to find what these values should be so that h of x is continuous everywhere. Or I should say continuous everywhere, which means for all real values, of x. Which means that if I plug in any real number for x, then my function is continuous everywhere, right? Now, the first thing you should ask yourselves is, what does it mean to be continuous? Well, many of you may say, oh, it's a graph where everything is connected. There's no jumps, there's no holes, there's no breaks, right? And I would say, yes, that's true. But for this type of problem, right, we're looking for particular values for constants. So I want more of the algebraic version of it. And the algebraic version is using limits. It's saying that the limit as x approaches some value for my function has to equal the value of the function. This means f of x is continuous at x equals a. That's literally what this mathematical statement means. This mathematical statement means f of x is continuous at x equals a. Means that my limits of my function as x approaches a is exactly getting to the value of the function at a. In other words, if I were to draw it, it would be a smooth curve. That's basically what I'm saying. When you say something has a smooth curve, connected curve, you're basically stating this every time. This is the mathematical perspective, and the other perspective is more the intuitive, graphical perspective. So basically what I want to do is I want to show this to be true. I need to have this to be true. Now, if we study this piecewise function a bit more, right, we see that for each function here, right, what kind of functions do I have? For this top one here, this is a linear function. So we know linear functions are continuous. They're straight. There's nothing fishy about them. It's just a straight line. So it's continuous. The next kind of function is a quadratic, and quadratics are continuous. It's a polynomial. And again, I have a linear function. So each of these pieces themselves individually are continuous. The problem exists when at those junctures. What are the junctures that we're talking about? Is that x equals 1, right? There's there may exist, because at x equals 1, it's like a boundary, right? To the left of 1, I get this function. To the right of 1, I get this function. But I want it to be continuous. I want it to be a smooth, connected piece. So the question is, what makes a and b? What kind of value should a and b have so that it's a continuous function? So I have to show two things. Show that the first thing is that the limit as x approaches 1, right? As x approaches 1 for h of x in this case has to equal h of 1. So I need to show this. And the second thing I need to show is that the limit as x approaches 2, because 2 is the other point, right? To the left of 2, I have this function, and to the right of 2, I have this function. So I have two different functions to the right and to the left of 2. So I need to find what those a and b values should be so that it's a nice one connected piece. This is f of h of x equals h of 2. So I have to show these two things. Must be true. Okay, so first of all, let's look at this first thing. So I want my limit for my function h of x to equal h of 1. So I'm going to find out each of these pieces, right? So h of 1. First, let's find h of 1. What's h of 1? So if I were to plug in 1 for my x value, and I plug it in here, is 1 less than 1? It's not. So then what do? I skip. Does 1 satisfy this condition? Well, clearly it does, because x is here is less than or equal to 1. So if I plug in h of 1, what should I be using? I should be using this value here, this function here, and I write this is a times 1 squared plus b, which equals a plus b. So if I were to plug in 1 into my function, I should get a plus b. So the second thing is that I want my limit to exist first. So if it exists, what does that mean? That means that the left-sided limit equals the right-sided limit. So first I must find the left-sided limit. So if it's the left-sided limit, 1 is approaching, my x values are approaching 1 from the left. And I get h of x. But if I approach 1 from the left, that means that I am less than 1. So if my x values are less than 1, then I'm using 2x. So this will be the limit as x approaches 1 from the left of 2x, and I get 2. So my left-sided limit equals 2. Now what's my right-sided limit? If I approach 1 from the right, so it's kind of repetitive to say h of 1 equals a plus b, and the limit from the right of it is a plus b as well. But this redundancy should happen. It should happen. And so I want all of this to be equal. I want the value of the function to equal the right-sided limit and to equal the left-sided limit. That's what this statement means. So then out of all of these three statements, what's the result? The result is that a plus b equals 2. That's the result. The left-sided limit must equal the right-sided limit in order for this to equal the value of the function. So I got one equation out of this, but I have two distinct variables. So that's where I need. So Brielle asked, would 1 from the left be substituted as -1? Definitely not. This sign here is not negative. It does not indicate that 1 is negative. It just indicates, it's just an indicator that I'm approaching 1 from the left side. It's just a notation. This negative symbol as a superscript just indicates that I'm approaching 1 from the left side. And this plus here indicates that I'm approaching 1 from the right side. If I'm approaching 1 from the left side, that means I am smaller than 1, or less than 1. And if I approach 1 from the right, that means that I am slightly more than 1. I'm greater than 1. So that's where this symbols come into play. It does not mean that the 1 is positive. Well, 1 is positive. And it does not mean that 1 is negative. It just means that I'm approaching 1 from the left side. So after all of this is said, I know that a plus b equals 2. So I know that, right? But the problem is I only have one equation and I have two variables. I can't solve for a or b just having one equation. So I need another equation. That's where the second limit comes into play. So I'm exactly going to be doing the same setup, the same thing. But the only difference is I'm using 2 now instead of 1. So I'm going to do the exact same thing. I'm going to say h of 2. What's h of 2? How would I evaluate h of 2? So h of 2, I would plug it in, right? Well, 2 is not less than 1, so I skip. Is 2 in this condition? If x equals 2, does this satisfy this condition? It does. So if I plug it in, I get a 2 squared plus b, which equals 4a plus b. So the value of the function at 2 is exactly 4a plus b, whatever that may be. Next, then I find the limit as x approaches 2 from the left of h of x. So I'm doing the exact same thing, except that now this 1 becomes a 2 because I'm dealing with the limit as x approaches 2. But now I'm approaching it from the left side. So if I'm approaching 2 from the left side, that means that my x values are slightly less than 2. So if they're slightly less than 2, right, I'm in this condition here. So I'm using this again. So I'm using the limit as x approaches 2 from the left of ax squared plus b, which is exactly what I get up here. Like I said, this will happen either on the left side or the right side, right? This may happen where the value of the function is exactly the same thing as the left side of the limit or the right side of the limit. In this case, the value of the function at 2 is exactly equal to the left side of the limit at 2. And do one more thing. I have to do the limit as x approaches 2 from the right. And I get the limit as x approaches 2 from the right. If I approach 2 from the right, that means I'm slightly bigger than 2. So x is greater than 2, so I'm using this condition is met. So this becomes the limit of 4x. And I get 8. And so now I have these three statements that must all be together. They must all equal because I want this to be continuous at 2. So then what do I say? What's the result? The result is that 4a plus b equals 8. So from on my first case, this limit gives me this result, a plus b equals 2. And the other limit that I must hold in order for this to be continuous, I get 4a plus b equals 8. So now look what I have. I have two equations and I have two unknowns. So then this is exactly right. This is the systems of equations. So see, this is where algebra comes back into play. And I'm not even and this like this exam, or this is not on algebra. This is not an algebra exam, but you need algebra in order to do these things. So a lot of mathematics builds upon previous knowledge, builds upon previous skills. So when you learn about how to factor, you don't learn about factor just for the sake of it. You learn about factoring because you're able to do now higher level, more interesting things. You're able to find limits. But in order to find limits, you have to be able to do the fundamental, rudimentary stuff, right? So now this comes back to play. You're like, okay, what's A and B? But I have these two equations. For those of you who know how to solve equations, which system of equations, which you all should know, I know that I can solve this. I can solve this system because it's a system of linear equations. And I got a plus b equals 2 as my first equation. And I have 4a plus b equals 8 as my second equation. And at this step, I can solve it using graphing or using substitution or using elimination, right? So either way, whatever is more convenient for you. At this step, what I would do is I would eliminate, and I can simply eliminate this by multiplying. You see how the b's here? They're both the same coefficient of 1. But one of them is positive, the other one is negative. So I can make the first one negative, and then I can add them. So if I do that, if I multiply this whole thing by negative 1, what do I get? I get negative a minus b equals negative 2. And then I get at the bottom, I didn't do anything to this. So I didn't do anything to the second equation. And now I can do what? I can add both equations together. And when I add them, the b's are eliminated. Negative a plus 4a is 3a. And negative 2 plus 8 is 6. Divide by 3. Divide by 3. And what do I get? I get that a equals 2. So great, I found what a is. A equals 2. And now I want to find what b is. And how do you solve the system of equations? After you find one of the variables, you plug in the other variable into one of the equations that you started with. And the easiest one to start with to use is the first equation, a plus b equals 2. So if I plug in a to this equation, I get 2 plus b equals 2. But what value should b equal? It has to equal 0. So if I make a equals 2 and I make b equals 0, I would have a continuous function everywhere. And how do you know that? Well, I just proved it, showed you basically using the definition of the limit, definition of continuity using limits. So if I make a equals if I make a equals 2 and b equals 0, my limits will equal the function at 1, and my limits here, right side and left side, will equal the function at 2. And basically, I am done. Great. I'm glad you understand. So that's the idea. And if I were to sketch this graph, right? And I can do that. I think we can do that quite simply, right? If I sketch this graph, you'll see that everything's connected. Okay. Well, I'm glad you guys are enjoying learning calculus on a Sunday night. Um, yeah, we'll see if I can do more of this. I can't guarantee it, but I definitely have this in mind, right? To do more of these kind of things because you know technology now it's so helpful. If used properly, you can do so much good. Um, so once this is clear, right? Now what I'm gonna do is I'm gonna plug in 2 here. And because this is 0, I can kind of forget about this. Okay? And all I'm gonna do now is I'm gonna sketch the graph of this function. And then hopefully you'll see visually why now it's continuous. Okay? So we've already accomplished our goal, a equals 2 and b equals 0. And I'm pretty much I'm satisfied with that. So now all I'm gonna do is sketch the graph, and hopefully that gives you even more of a it's even more convincing that it's continuous. So how would I do that? So x is less than 1. My marker is fading. Okay, so I care about 1. I care about things less than 1. And I care about things between 1 and 2. And I care about everything to the right of 2. Right? So now I have this function here. And I know that if x is less than 1, my function is 2x. So then how would I sketch that? Again, this is just a sketch. It's just a rough sketch, right? So at 1, what's my function? So at 1, remember, at 1, what's my function? It's 2 times 1 squared, which equals 2. So at 1, I have the function, the value of the function is 2. So I close the circle here. Now, what happens to the left of 1? I have 2x. 2x is what? A function whose y-intercept is 0 and whose slope is 2. So I go up and over 2, and I get this line. So to the left of 1, I have the line 2x. And then between 1 and 2, right? So at 1, my function is 2. At 2, what's my function? 2 times 2 squared, which is what? 8. So my function is somewhere up here. I'm probably gonna like overdo it, right? But again, this is not drawn to scale. Definitely not drawn to scale. But if I were to draw this, I have something like this. So at 2, I'm up here. And 2x squared is a quadratic. The quadratic looks something like this. It's a quadratic, right? It's a parabola. But I only want the piece between 1 and 2. So I have something that looks kind of curved like this. And then from 2 onward, I have 4x. And 4x, what happens? I start at here, right? What happens at 2? 4 times 2 is 8. So I'm here, and I move up. Of course, I'm going through this, right? But this is a rough sketch of this piecewise function. Now all the pieces are connected. And that's only possible if a equals 2 and b equals 0. Any other values, I would have different pieces, and there will most likely be a jump discontinuity at 1 and 2. But now because these values are specified based upon the definition of a limit, I have a, even though it's not completely like, in terms of like drawing this, I have to kind of like draw straight, smooth, and then I kind of have to move a little different, and then kind of like, sketch it a little. It's not clear. I mean, it's not smooth. It's kind of jagged a bit, but it doesn't matter. It's still continuous. Yes. So that this means that the function is continuous. So this is just to give you a visualization of it. So it's more convincing as to why I got a equals 2 and b equals 0. Okay. Will I ask you to graph these values? I mean, you should be able to. You should be able to graph any piecewise function, right? But more importantly, like I said, you should be able to do everything that we've been speaking of for the past 3-4 weeks. So piecewise functions are definitely important to know how to graph, how to visualize, um, for continuity purposes. So this is usually it's huge. Piecewise functions are a huge topic that needs to be understood prior to calculus, right? Usually you learn this, you should have learned this in pre-calculus, um, because again, continuity is very prevalent using piecewise functions. All right. So that's how you find the values, and I think that's pretty good example. Um, so I guess I'll do one limit. Oh, that's a very good question. So what if you have a hole, right? What if you have a hole and you want to fill it in, quote unquote, right? So I'll talk about that real quick. And it's very simple how to fill it. So I'm gonna give you a so holes occur, right? Holes occur when you have rational functions, right? So I'm gonna do a rational function real quick. So the example of that, right? If I have like r of x equals x squared minus 3x plus 2 over x minus 1. So I'm gonna use minus 2. So I have a rational function here, right? And then what do you realize? You realize that I can factor the top. So I can factor this as what? X squared minus, sorry, x minus 2, x minus 1 over x minus 2, right? And then you would be tempted to do what? You would be tempted to cancel out the x minus 2's, correct? Yeah, so Courtney, this is exactly what we're covering. Holes are removable discontinuity. So I'm gonna go for 10 more minutes until 9 p.m. Okay. So if you have any other questions, please write them in the comments to see if I can finish in 10 minutes. And if you really have any pressing questions, you can come see me before class. I should be there as early as possible before class. So probably 7:15. I'll probably get there around 7:15. So holes, right? Holes are just another word for what's called are really removable discontinuity. Okay, so holes are removable discontinuities. Removable discontinuities are holes. We have an example of a function that has a hole, and it has a hole at a very particular point. So if you study this, right, you factor this out, and you would be tempted to cancel the x minus 2's because that's what you normally would do, right? However, you have to be a little more careful as to when you're able to do so. You're only able to divide the x minus 2's when the x minus 2's are non-zero, meaning that this value here is not equal to 0. When does this value equal 0? X minus 2 equals 0. I mean, yeah, x minus 2 equals 0 when x equals 2. Isn't it true? So if I plug in 2 here, I'll get 0. But that's the problem. If x equals 2, then I have 0 in the denominator, and that's undefined. Do you see? Now, what if x does not equal 2? So let's say I have x values here that doesn't equal 2. Because these x values don't equal 2, that means that x minus 2 is not 0. Because x minus 2 is not 0, I can then cancel these out. So then really this function here, I'm going to call it r of x, right? This function here can be actually written as a piecewise function. And what are the pieces? The first piece is just going to be x minus 1. But that's if what? That's if x does not equal 2. So if x does not equal 2, I can cancel these out, and I'm left with x minus 1. But what if x does equal 2? What's the problem with that? If x does equal 2, then what? My denominator equals 0, and my function is undefined. What does that mean? That means that at this point I have a hole at x equals 2. There's a hole. Now, graphing it might give you a better understanding. What's the graph of this? X minus 1. Well, that's pretty simple. It's a linear function whose y-intercept is -1 and whose slope is 1. So my y-intercept is -1. My slope is 1. But what is the problem? The problem occurs where? When x equals 2. Everywhere else, it's a straight line. But at 2, so this is 1, right? And at 2, what happens at 2? Open circle. There's a hole. Hence undefined. That's where the undefined comes into play. Now, the question is, how can I remove the discontinuity? Well, I can remove it by filling this in. But how do I fill this in? I have to figure out, what would this value be? What would this be? If I were to fill it, and if I were to go straight through, right? What would this be? And it just so happens that whatever this value is exactly the limit at 2. So then the question is, what is the limit as x approaches 2 of my function? X squared minus 3x plus 2 over x minus 2. And this is exactly the kind of limit you would probably see, right? That you've seen already. You probably will see this tomorrow, solving a limit such as this. But you see how this now has more of a significance? Because you're not just finding the limit for the sake of it. You're finding the limit so you can remove, quote unquote, the discontinuity. So it has more significance to it. But evaluating this should be simple, shouldn't it? So you recognize I can't just plug into. What should I do? Factor it. So I get the limit. I get exactly what I just wrote up there. X minus 2, x minus 1 over x minus 2. The x minus 2's can cancel. Why can they cancel? Because my x values approach 2. They're not equal to 2. They approach 2. So then these expressions here are not exactly 0, but they're approaching 0, but they're not 0. So I can cancel them, and I get the limit as x approaches 2 of x minus 1. And now this is nice because I can just plug it in. And so then when 2 goes in, when I plug in here, 2 minus 1 equals 1. So then what do you realize? What I realize is at 2, what should this be? It should be 1. So how would I remove the discontinuity? I would say, hey, at x equals 2, make this equal to 1. And I removed it because now I filled it in, and now it's continuous. So for jump and infinite discontinuities, you can't remove it. Hence, that's why these are different discontinuities. One such discontinuity is removable. Jump discontinuities and infinite discontinuities aren't just being. You can't just remove them. You can't just make them disappear. So for removable discontinuities, this is the way you do it. You find what the limit is, and then you just basically just say, hey, make that at 2, just make it 1. Okay, so that's a very good question about holes and what they're called, also known as removable discontinuity. Okay. Okay, so I'm gonna do a absolute value, a limit, and we can call it a night. All right. Okay, so I'm gonna do one with absolute value. Let's see if I got a good see if I can find a good one. Okay, so what if I have like this, something like the limit as x approaches 3 from the left of the absolute value of x plus 3 over x plus 3. So what is this limit? So what makes absolute value limits of absolute value a little more tricky, it has to do with which side am I approaching the value for x. So depending upon which side, whether on the left side or to the right side, it's going to affect what this absolute value is. Now, that's why it's important to understand the absolute value is really a piecewise function. What is a piecewise function? So the absolute value of x plus 3, right? So actually, what I'm going to do is I'm going to represent this graphically. What's the graph of x plus 3? And hopefully with that, you'll see it a little more clearly. So if you remember from pre-calc, right, transformations of functions, the parent function here would be, what would be the parent function? Y equals absolute value of x. And we should all know what the absolute value of x, the graph looks like. It's like a V, right? Centered at 0. But what am I doing to the parent function? I am moving it 3 units to the left. So instead of having the little v at 0, it's going to be at -1, -2, at -3. I'm going to have the same thing here. See that? Right? So that means that to the right of 3, my function is y equals x plus 3. That's if my x values are bigger than 3. Negative. Sorry. This should be -3. Sorry, this should be minus 3. Yeah, so actually, yeah, let me just rewrite this. So this is what I meant to say. Sorry about that. So x minus 3, right? So in order for this to be good, so let me draw this again. So the only difference is now that the parent function is the same. It's absolute value of x. And x minus 3 means I am shifting the parent function to the right by 3. So 1, 2, 3, okay? So I have the same thing here, right? So I have these two branches, right? So to the right of 3, what's my function? It's x minus 3 if x is bigger than 3 or equal to 3. But what happens to the left of 3? Well, I get what's called y equals negative x plus 3. And this is if x is less than 3. So if I'm approaching 3 from the left, right, what is absolute value of x minus 3? It's actually negative x plus 3. So this becomes the limit as x approaches 3 from the left. This here is negative x plus 3 over x minus 3. See if I use another marker. So this is where it might be the difficulty, right? So this becomes the limit as x approaches 3 from the left, right? But then what do we recognize? I can factor out a -1 and I get x minus 3 over x minus 3. But the x minus 3's what? They cancel. And I'm left with -1. So the limit of this absolute value expression here is -1 if my x values approach 3 from the left. So then the question would be, what would happen if it approaches 3 from the right? I'm gonna draw. What would happen if I find the limit as x approaches 3 from the right? Well, if I approach 3 from the right, my function is just simply x minus 3. And so I'm left with the limit as x approaches 3 of x minus 3 over x minus 3. But what's nice about this is the limit. Well, if I cancel this, right, I get the limit as x approaches 3 of 1, because x minus 3 over x minus 3 equals 1. But the limit of 1 as x approaches 3 is just 1. So the left side of the limit equals -1. The right side of the limit equals +1. So then what would be my conclusion? My conclusion would be that the limit as x approaches 3 for x minus 3 over x minus 3 does not exist. It doesn't exist because my left side of the limit does not equal my right side of the limit. So I try to maybe explain what is the absolute value of x minus 3, right? The different branches, right? But the more proper way to do this is viewing the x minus 3 as a piecewise function. So x minus 3 is negative x minus 3 if x is less than 3. And it's regular x minus 3 if x is greater than or equal to 3. And we put this equal sign just to indicate that if I plug in 3, right, I should get 0 at 3. That's where the equal sign comes into play. But the idea is that when my x value is less than 3, I have negative of whatever the inside expression is. And if I have x being bigger than 3, then it's just regular x minus 3. So this is where knowing what absolute value is really, as a piecewise function, really matters, really counts here. It really counts when you have to find the limits. Because once I have this understood, then finding the limits of the right side and left side, and you see why they're different. You would see why they're different. Okay? So any last questions? If you have any other questions, let me know now. If not, I'll see you all tomorrow. Thank you all for those who are endured with me for this hour and 18 minutes. I thank you all. I hope this was helpful in some way. Okay? Would you have to write a piecewise notation for the test? Well, I'm not asking you for the answer as a piecewise function, but I would say that having this notation clear would help you on the test, especially solving limit, um, finding limits where absolute value is in them. So if you're able to know this, if you're able to express this, right, and understand this, it's really about understanding. So this piecewise notation, I would say, is very helpful to solve such a problem. All right. Anything else? So if not, then hope you all have a very good night. Study, don't study too much, don't cram, because that doesn't really help at the end. It's all about being confident with what you're able to do. That's basically what you should be able to strive for. And the only way to really get to confidence is to practice enough that you got this, all right? All right, guys. So I'm glad you guys had fun with me. Hopefully, we'll have fun tomorrow. Okay. See you guys. Bye bye.